In part 2 of Moles and More, we're going to look at the relationship of moles in chemical equations and learn how to use moles so that we can understand the stoichiometry of a given reaction and how we can use that to make products. The first thing that we should address is what really is the nature of a chemical equation. Well, we can define it as a process in which one or more substances is changed into one or more new substances. That change can only be effected if we break bonds between existing substances and then form new bonds to create new substances. In this process, we go from reactants to products. And if we consider the reaction of hydrogen gas with oxygen gas to form water, we can realize that there are actually different ways of representing this reaction. We could think of it as combining molecules. We could think of it as being written in its chemical notation, or we can think of it actually in terms of space-filling molecules where we actually see our reactants and our products. The nice thing about these space-filling molecules is that we actually can visualize better how bonds need to be broken and reformed to create new things. But of course, the most common way to write a chemical reaction is to use the 2H2 plus O2 yields 2H2O. We need to be able to read these equations. And what is the nature of reading an equation? Well, it's understanding every part of it and how it works. What are we actually combining in what quantities? Because when we say 2H2, what does that refer to? Does it refer to molecules? Does it refer to moles? Does it refer to grams? Well, the truth is it can refer to any of these. But honestly, the one that's most useful to us is 2 moles of hydrogen plus 1 mole of oxygen makes 2 moles of water. Now, grams are also useful, but we have to do the conversion from moles to grams in order to know that 2 moles of hydrogen equal 4.03 grams of hydrogen, and so on. Here again we have our space-filling model, and I would say that the most important mistake never to make is to say that 2 grams of hydrogen plus 1 gram of oxygen makes 2 grams of of water. It can be tempting to go down that path, but if you remember that every mole quantity is actually associated with a different gram quantity, and when you convert moles to grams, you're going to get different numbers, then you will understand that you cannot say 2 grams plus 1 grams equal 2 grams as written here. Now we can actually tackle this stoichiometry idea by considering the equation again of the formation of water. This time it's not balanced, so its stoichiometry would be out of whack. We need to balance it, and then we can understand how our stoichiometric coefficients in a balanced equation represent the correct or necessary number of moles of reactants and products. So here we have it back in its balanced form, and we see that 2H2 plus O2 yields 2H2O. Now, stoichiometry is a big word with a simple meaning. It just means the coefficient, the number relationships between products and reactants, or even products and products. When we know these coefficients, when we've figured out what they are, then we can determine something called the mole ratio. The mole ratio relates the amounts in moles of any 2 substances in a chemical reaction. So let's say we have moles of A, and we want to convert to number of moles of B. Well, we bring back our friend the conversion factor, and we say however many moles of B we have in relationship to moles of A as our conversion factor. When we multiply moles of A times moles of B over moles of A will cancel, and we'll get moles of B. Now that's pretty abstract, so as we go forward here, we're going to see some real concrete examples. The driving question of stoichiometry, and the reason we want to know these mole ratios, is chemists are generally interested in how much product can be formed from specific amounts of reactants. And we can use this stoichiometry, this numerical relationship, to determine the above. At least that's our question. Can we do it? Yes, absolutely. We can use this mole method, these mole ratios based in the stoichiometric coefficients, and we can come up with ratios that will allow us to figure out how much of a particular product we will get when we put in a certain amount of a given reactant. Now for this reaction here, the combustion of methane, CH4, in oxygen to produce CO2 in water, we see that our stoichiometric coefficients are 1, 2, 1, and 2, respectively. So anytime you have a number before a particular molecule or compound, that's its stoichiometric coefficient, and if a number is not written, it is implied that that number is 1. Here we are back with water, the formation of water, so we can actually set up some conversion factors. We can say 1 mole of O2 for every 2 moles of water, or 2 moles of water for every 1 mole of oxygen. This ratio, this is the real summary or object lesson here, will allow us to convert from moles of one substance to moles of another substance, I would say in either direction. So in other words, if you look at the picture, we can say for 1 mole of oxygen, we're going to get 2 moles of water. If we want to go in the other direction, we can say for every 2 moles of water we put in, we could get 1 mole of oxygen back, because reactions are typically reversible. Now, here's where the rubber hits the road. We're going to do a real problem involving a mole-to-mole ratio, and it's going to involve ammonia. So the situation here is we're in the lab, let's say. You have your goggles on, you're ready to go, and you're going to use 6 moles of hydrogen with a major excess of nitrogen gas, more than you would ever need, and you're going to try to figure out, before you actually conduct the reaction, how many moles of ammonia you can actually get. Well, the first thing you need to do is balance this equation, because if you inspect this equation, you're going to notice that it is definitely not in balance, and we need to add some coefficients in order for it to be balanced. Then we're going to use our mole-to-mole ratio to see exactly how much ammonia we can get. So here is the equation balance. Notice we put a coefficient of 3 in front of the hydrogen. We've left the nitrogen alone, and we've put a coefficient of 2 in front of our ammonia, and everything is now nicely balanced. We were given that we have 6 moles of hydrogen. So now what's our mole-to-mole ratio going to be? Well, we could say that we get 2 moles of ammonia for every 3 moles of hydrogen. Or we could look at that the other way around, but let's just put them out here and figure out what the right way is to write this so that our unit cancels and our moles of hydrogen cancel, I should say. So we take our 6 moles of hydrogen and we say, okay, we're going to get 2 moles of ammonia for every 3 moles of hydrogen that we put in, 2/3 basically. So the most we could ever hope to produce from 6 moles of hydrogen is 4 moles of NH3 based on this 2/3 ratio. We need a strategy to tackle calculating amounts of reactants and products, because as we go through using stoichiometry to evaluate amounts of reactants and products, we're going to find that things can get a little more complicated. So let's look at some of the really common steps we need to perform and what order we need to perform them in. Well, first of all, we need to make sure the chemical equation is balanced. Often, we're going to be given not mole quantities, but gram quantities. And we want to make sure we know how to convert those given gram quantities into mole quantities. Finally, we're going to use those stoichiometric coefficients in the balanced equation to develop a mole-to-mole ratio and calculate the number of moles that could potentially be produced. And then finally, we may be asked to convert back to grams. So we're going to convert the moles of whatever product it is we were trying to calculate. And once we have calculated that, we may convert that into grams. Now this figure looks a little bit complicated, but I actually like it because I think of these stoichiometric problems as following the yellow brick road. So let's say we are starting from mass of compound A, as you see in the upper left of this diagram, and we want to get to the mass in grams of compound B, as you see in the upper right here. Well, we have to go from mass of compound A to moles of compound A to moles of compound B to mass of compound B. So we're going to be going back and forth here. We're going to go from mass to moles using our molar mass. Then we're going to use the mole ratio to figure how many moles of compound B that we could actually get. And then we're going to go from moles back to grams, again using our molar mass. You have done this. The only real new twist here is adding in the mole ratio. So now, I said before that you can't combine 2 grams of hydrogen and 1 gram of oxygen and get 2 grams of H2O. And now I'm going to set out to prove it to you. And we're going to figure out how much water we can actually make from these amounts. We can also evaluate one of them is going to run out first. So we're going to ask ourselves, how can we figure this out? How do we know which one is going to run out first? Well, we're going to follow the yellow brick road like we saw in that last figure. We're going to go from grams to moles, and then we're going to use mole-to-mole ratios. So the first question we need to ask ourselves is how many moles are there in 2 grams of H2, and how many moles are there in 1 gram of O2? We're going to use the molar mass to get from grams of hydrogen to moles of hydrogen. And we're going to use the molar mass of oxygen to get from grams of oxygen to moles of oxygen. Once we do the math, we're going to see that 2 grams of hydrogen produce 0.99 moles of hydrogen gas. That's almost 1 mole. And that 1 gram of oxygen times its molar mass produces only 0.03 moles of oxygen gas. So based on a preliminary inspection of our balanced equation, certainly looks like we're going to run out of oxygen first. Because based on the mole ratio, we see we need 2 moles of hydrogen for every 1 mole of oxygen. But the fact is, if we look at the ratio between 0.99 moles of hydrogen to 0.03 moles of oxygen, we have approximately 33 times as much hydrogen as we do of oxygen. That means we're going to run out of oxygen way earlier, and we're going to have a lot of hydrogen left over once that oxygen is used up. So now we can use the information that we just calculated to figure out exactly how much water we can make if we react 2 grams of hydrogen with 1 gram of oxygen. We're going to need our mole-to-mole ratios, and we're going to need the numbers that we just calculated, which is 0.99 moles of hydrogen and 0.03 moles of oxygen. So we know, using the mole to mole ratio, that we will get 2 moles of water for every 2 moles of hydrogen. That's basically the same as saying whatever mole amount of hydrogen we put in, we're going to get the same amount of water coming out, because 2 to 2 is really the same as 1 to 1. However, with 0.03 moles of oxygen, we know we get 2 moles of water out for every single mole of oxygen we put in. And when we do that math, we realize we're actually going to get 0.06 moles of H2O when we put in 0.03 moles of oxygen. Now, if we look at 0.99 moles of water being made versus 0.06 moles of water being made, as we just said, we can clearly see that we're going to run out of oxygen before basically we're going to run out of oxygen, and then the reaction is going to stop because hydrogen isn't going to have anything to react with. That means that 0.06 moles of water is the most we can make with these gram amounts, and oxygen, therefore, is the limiting reagent. This leads us into a further analysis of limiting reagent and something also called theoretical yield, which is usually the gram amount that we can possibly hope to achieve in an ideal reaction. So now we're going to use both limiting reagent and theoretical yield to tackle the problem of how much carbon dioxide we could actually form if we combine 50 grams of methane and 150 grams of oxygen. I should have said how much carbon dioxide could we theoretically form, not actually form. So here we are, back to our methane combustion reaction, which we saw previously. And we're going to follow a series of steps in order to figure out what the theoretical yield of carbon dioxide could be. Step 1 of this process, since we're given gram amounts of both reactants, is to take each of these reactants and convert them both to moles. It's critical to do both. Then you can use the mole to mole ratio, just like we did for water, to determine how much CO2 could possibly be formed for each reactant. Then we're going to be able to see in step 3 what is the limiting reagent, because whichever reagent produces the fewest moles of CO2 is the limiting reagent. And then finally, since we want to know, based on that limiting reagent analysis, how many moles of CO2 we could possibly form, then we can convert that back to grams of CO2. So here we have it. If we combine steps 1 and 2, we'll see that we can take 50 grams of methane, multiply by the molar mass, get the number of moles, and then use the mole to mole ratio, which happens to be 1 to 1, using this balanced equation, 1 mole of CO2 for every 1 mole of CH4. That means we'll get a maximum of 3.117 moles based on the amount of methane that we're putting in. Now for 200 grams of oxygen, we have to use the molar mass of O2 and multiply that to get 6.25 moles of oxygen. Now our mole to mole ratio is actually 1 mole of CO2 for every 2 moles of oxygen. This is going to give us 3.125 moles of CO2. So what is our limiting reagent? Well, as I said, whichever reagent produces the least moles of CO2 is our limiting reagent. That's the most amount of CO2 we can make. And we need to evaluate it in both cases so we know what the maximum amount of CO2 is. And when I say in both cases, I mean for each gram amount of reactant. Now, we've figured out that we can theoretically make 3.117 moles of CO2. So we're going to multiply that by the molar mass, and we're going to get 137.2 grams of CO2. This, my friends, is the theoretical yield.